This is Physics 106, Chapter 18. This chapter is ray optics. So the previous chapter was wave optics. So this is the second model of light. There's still one more, believe it or not. When we start doing quantum physics later on, we'll learn the quantum mechanical model of light. So in order to understand light, three models. All right, so here's the objectives. We're going to use the ray model of light, how light is emitted from objects, how we see objects, how shadows are formed, understand the law of reflection in image formation in mirrors, understand and apply the law of refraction, understand total internal reflection and the concept of critical angle, that's fiber optics, understand image formation by lenses and how to use graphical ray tracing, understand image formation and ray tracing for mirrors, spherical mirrors, and use the thin lens equation to analyze image formation by lenses and mirrors. Now, you'll be doing a lot of ray tracing, so you'll need a ruler and you really need graph paper. So I strongly recommend you download some graph paper and print it out. Also, this is a chapter where you want to make sure that you read the chapter. I mean, this is a chapter where you want to really read the textbook carefully. There's a lot of background conceptual material, which I'm not going to discuss. I'm just going to do the things that I feel that are challenging for students. And so make sure you read the conceptual material for any of this makes sense. All right, let's go. So here is the ray model of light. Number one, light rays go straight. And you can demonstrate that with a laser pointer. Go outside and when it's dark and point a laser pointer up somewhere and you'll see a nice straight line. Number two, light rays can cross. They don't interact at all. They just cross each other. So there's no interaction. Light rays travel forever, number three, unless they interact with matter. Now there's four ways that light rays interact with matter. So number one, the light ray can reflect, like from a mirror. Number two, it can refract. Let's say this is air, let's say this is water. You see the little bend here. Number three, it can scatter, so it can just bounce off, let's say. Number four, it can be absorbed by matter. And we'll discuss these two in detail. Number four, any object is a source of light rays. For example, how do you see me? Because there's light from the ceiling lights, and they hit me, they reflect off of me and bounce into your eyes. Number four, what do eyes do? Eyes focus diverging rays of light. That's how we see. All right, here's a question for you. So just make this longer, a long, thin light bulb illuminates a vertical aperture which is located a short distance away. Which pattern of light do you see on a viewing screen behind the aperture? So pause your videos and figure that out. All right, this is the answer. And here's why. So let's pretend, all right, so this is the screen, and let's say that this is the vertical aperture, the slit, and here's the long light bulb. Well, all right, so we're looking down on it. So rays of light, they go here, and everywhere in between, right? So we're going to get something like that. But then they're going to go up here, right? So just going to form a nice square. So let's talk about the reflection. So reflection off of a shiny surface, like a plane mirror. What do you notice? So hopefully you notice that this angle equals that angle. So that's the law of reflection. Now, something you need to be aware of. For this entire chapter, whenever we discuss angles, the angles are always relative to the normal. And remember, normal means perpendicular. So here's the normal, and the angles are relative to this. So we don't care about that and that. I mean, we could, but we just don't, all right? Angles always relative to the normal. So theta incident equals theta reflected. That's all there is to it, okay? All right? So let's talk about a plane mirror, all right? A plane mirror. Well, what do you notice? First of all, look, the light rays reflect off of the mirror. But according to us, we think, the image is here, right? So here's the thing. These are not real light rays, right? We always draw real light rays with a solid line. We always draw projections or whatnot with a dotted line. So if you have an image formed by not real light rays, it's called a virtual image. So I hope you're reading the book and you can pick up all this vocabulary. All right, so there you go. So number one, we have a virtual image, and we think it's behind the mirror. Number two, and here's some things that you should pick up from your reading as well. So they'll always use S for the object distance. The object distance is the distance from the object to the mirror or lens or whatever you're talking about. They'll always use S prime for the image distance. You'll see that through the entire chapter. So it looks to me, and hopefully, so S equals S prime for this plane mirror. The third thing, hopefully you'll notice, that this line between the object and the image, it's perpendicular to the plane mirror. So that's really all there is to say about plane mirrors. Okay, next topic, refraction. I'm sure most of you are familiar with this. If you put a pencil in a beaker full of water, it looks like the pencil is bent when it hits the water. Well, what's the deal with that? Well, that's what we're going to talk about now. All right, so here we go. So here, this is air, this is water, and you'll see that here's a nice ray of light. And what happens when now look at, some of it reflects, so we still have that equals that, no kidding. But some of it doesn't reflect. It goes, we call it refract, so it goes in the water. Now what do you notice about the angle? So see, this ray, this refracted ray bends toward the normal. So that's the important thing, all right? The refracted ray bends toward the normal. You can see that, right? It bends toward the normal. So that's what happens when it goes from air to water. Well, how about when we're going from water to air? So now this is the flashlight. So I have the incident ray. Some of it reflects, right? So this theta 1 equals this theta 1. But look at theta 2. Look what it does. Now the previous one, it bent toward the normal, right? But look at what this does. It bends away from the normal. What's the deal? All right. Well, how come? Well, this is all incorporated into what's called Snell's law. Remember, this is the index of refraction. So n1 sine theta 1 equals n2 sine theta 2. That's all there is to it. Okay. Now, you have to be really careful about one thing here. There's the convention. The convention is n1 is the ray of light that leaves from the light source. Right? So see here, this is n1, right? Air n1. And the water is n2. But here, the light ray is leaving from the flashlight. So this is n1, and this is n2. So you'll see that throughout the chapter. So just keep that in the back of your head, or front of your head, actually. All right. this whole business of refraction is responsible for the difference in actual depth and apparent depth of an object underwater. So don't worry about all these variables. Ignore all these variables. But, I mean, here's the thing. Here's a real fish. And so, you know, there's sunlight hitting the fish and it gets reflected. So watch. So this ray of light hits the air, and as we just saw a minute ago, it bends away from the normal, right? Here's the normal, bends away from the normal. This one, similarly, bends away from the normal. This one just goes straight up, right? That's the normal. This one bends away from the normal. This one bends away from the normal. Now look, how do you form an image of something? What you do is you backtrack on these outgoing rays and see where they intersect, right? That's how you form an image. So you always look at the outgoing rays and you see where they intersect. Well, by golly, they intersect here. So where does this belted kingfisher think the fish really is? Right there. That's the image. So, all right, so we would call this the real depth, and this is the apparent depth. And it's just due to the Snell's law, refraction. Okay, now all right, so now we've kind of shifted it by 90 degrees, all right? So this is water, so you can, let's say it's a fish bowl or something like that. So here's water, here's air. Now notice, so this is the object, let's say this is the fish. So this is a source of the light, right? The light from the, whatever, ceiling lights is reflecting off of this fish, so this is the source of the water. So that's why this is N1 and this is N2. If the source of the light were over here, this would be N1, this would be N2. But anyway, here's the formula, okay? So here's the object. So the light travels here, here's a normal. The light ray bends away from the normal. Same thing here. Here's the light ray, here's the normal, bends away from the normal. So how do you form the image? You look at the outgoing rays. So this outgoing ray goes here. This outgoing ray goes here. They intersect there. That's the image. That's where it appears the fish is, All right, so here's a formula. So S prime, remember that's the object, the image distance equals S, the object distance, times N2 divided by N1. And here, this is air, so N2 is 1. This is water, so N1 is like 1.33 or something like that. And so this is going to be 1 divided by 1.33. This is less than 1. So S prime is going to be less than S, right? So S prime is less than S. Yoo-hoo! Okay, so there you go. So this is a nice, so you use this again with like a fish in a fish tank or something like that with water. And this distance here is the S, right? This is the S prime. So we're really talking about along the optical axis, all right? These measurements of S and S prime are along the optical axis. All right. Here we go. You're underwater looking at a bird flying above. So you're in the water, right? The bird is above, okay? You will see the bird where? Greater distance than it really is, the same distance or a smaller distance. So think about that, think about these. But remember now you are, what's the object now? The object is the bird, right? So I would recommend you can either use this formula or just draw the picture. So please pause your video and figure it out. And be careful, what's N1 and what's N2. All right, so pause. Okay, so the answer is a greater distance. So there's a couple of ways you can do it. So here's the formula. But remember, the object is the bird. The bird is in the air, so that's N1, right? You are not the object, right? You're looking at the object. So you are N2, that's the water. So you can just use the formula, right? So S prime equals S times N2, 1.33 over 1. Okay, this is greater than 1, so S prime is greater than S, all right? So you'll see the bird at a greater distance than it really is. Now, some people like to draw pictures, which is fine. So pretend this is the bird, all right? So this is the front of the bird, this is the back of the bird. So here's a light ray coming from the bird. Here's the normal. Now what is it going to do? It's going from air to water, so it's going to bend toward the normal. So bends toward the normal, right? Same thing here, bends toward the normal. All right? Okay, now remember, we're down here, so we see these rays, right? These are the outgoing rays. So you go back up, go back up, and you see the front of the bird and the back of the bird. So it looks like it's higher, all right? Greater distance. Okay, here's kind of a neat little trick you can show your friends. You need a mug and a coin. Place a coin at the far end of the bottom of an empty mug. Sit in a position so that you are just unable to see the coin. Then, without moving your head, utter the magic word, refraction, as you pour water carefully into the mug on the near side. Pour slowly so the coin doesn't move. The coin becomes visible when the mug is filled with water. Why? So pause your video and think about it. Try to figure it out. All right. So here it is. So here's the empty mug, and here's the coin. So the light from the ceiling lights reflects off the coin. And let's just say, look at this ray. So this ray, right, you don't see it. That's what I mean by this, all right? Forget the artwork, right? You don't see it. It doesn't go into your eye, okay? Because you're sitting too low. All right, now here, though, you fill it with water. So what happens when you go from water to air? It bends away from the normal, right? So this same ray of light here bends away from the normal, and bang, it's going to hit you right in the eye. So it's just refraction. All right, let's do an application of this that's used all the time in, it's fiber optics, which is very popular in medicine and communications and other things. Okay, so here we have, this is air, let's say N2, and this is N1 fiber, some kind of a fiber, all right, just whatever, glass or something. So we want N1 greater than N2, all right? So again, N2 is just air, this is equal to 1, this is greater than 1. All right, so here's the object that's emitting light. So here, it just follows along the normal, right? So it just goes, you know what I mean? There's no reflection. Now here, a little bit of an angle. So most of it goes through, or we can say most of it is refracted, right? And it bends away from the normal. But some of it is reflected, not much, but a little bit. Then we go at a greater angle, and some of it is refracted, not as much as over here, right? And again, you can see it bends away from the normal, and more is reflected here than here. Okay, go even further, and you can see that a lot is reflected, and this is refracted. But notice, this refracted, this angle of refraction is 90 degrees. So if we can call that theta critical. I'll explain why in a minute. Now let's increase our angle even more. And what do you see? You see that none of it is refracted, right? It's all reflected. So if you want the light to stay in your fiber optic tubing, what do you want? You want the angle, the angle to be greater than this critical angle, all right? So this is theta 1, right? This is theta 1. So you just want that greater than theta critical, and it's always going to be reflected, okay? So that's called, guess what? Total internal reflection. So you don't lose any signal, right? You don't lose any light. So that's how fiber optics works, Okay, so how do you find the critical angle? Well, the critical angle, this is this is theta 1, and this is theta 2, the 90 degrees. So let's do it. All right, so this is just, Snell's law. So N1 sine theta 1 equals N2 sine theta 2. Now what we're saying theta 1 is theta critical. All right, that's when this occurs, right? And theta 2 is 90. Okay, well, what's the sine of 90? 1. So sine of 90 is 1. So therefore, you get sine theta critical equals N2 over N1. And that's all there is to it, okay? And look, remember, this is air. This is like glass or something. So this is always bigger than that, right? N1's always bigger than N2. So this is always going to be less than 1. Okay? So you can just say that. So in other words, so theta critical would be inverse sine of N2 over N1. And that's all there is to it. So there's a lot of important things here, right? The reflection gets stronger as you increase this theta 1 and da 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 da. Total internal reflection occurs when theta 1 is greater than that critical angle. So if you're designing a fiber optic, you've got to know this. All right, let's quit.